Hello everybody, welcome into another lesson. So today we are going to talk about indirect proofs. So up till now we've been dealing with direct proofs, such as using theorems and postulates and definitions and corollaries to prove other theorems or other facts. Indirect proofs are a little bit different in the sense that you need them sometimes because it's almost impossible to do a direct proof, and so you have to use backwards reasoning. So for example, we are given triangle XYZ right here. We're also given that the measure of angle X equals 100. What we have to prove is that angle Y is not a right angle. Well, that would pretty much be impossible to do a direct proof of. But this is where the indirect proof comes in for rather obscure facts. So how we do an indirect proof is it's in paragraph form instead of in two-column form, okay? And to start an indirect proof, what you have to do is actually start by assuming that the conclusion, you have to assume the opposite of the conclusion is true. In this case, the conclusion, what they want you to prove is that angle Y is not a right angle, okay? What we would have to do in this case is start by assuming that angle Y is a right angle. Assume angle Y is a right angle. So we're going to start there. Assume angle Y is a right angle. So what does that mean? Well, let's see. The measure of angle X equals 100. And the measure of angle Y equals 90, right? If we're assuming that angle Y is a right angle, that means the measure of angle Y equals 90. So we've started out by assuming the opposite of the conclusion. We basically state what that means. We basically have to work to show that our assumption contradicts either what's given to us or a known fact. In this case, we could show right away that we could say, but this contradicts the sum of the measures of interior angles of a triangle is 180. Therefore, angle Y is not a right angle. Okay, so let me go through this. To do an indirect proof, you start by assuming what you got to prove. You start by assuming the opposite of what you got to prove. And then you reason from there until you can contradict either given information, a known fact such as the previous theorem, postulate, definition, corollary, or both. So we started in this case by assuming that angle Y is a right angle. Well, the measure of angle X equals 100 and the measure of angle Y equals 90. But this contradicts the sum of the measures of interior angles of a triangle is 180, right? Because if you add X and Y together alone without even factoring in angle Z, you're already at 190. So, therefore, angle Y is not a right angle. In the end, you reason that what your assumption is false, so what you're trying to prove must be true then. That's all it is. That your assumption is false and what you're trying to prove must be true. That's really all this is. And I do have some more examples here today. No new theorems or definitions or anything. It's just we're going to use what we've learned, but let's do the next one. Let's see. Given n is an integer, so here's an algebra problem. Really starting to get into number theory more than algebra. We're also given that n squared is odd. What we have to prove here is that n is odd. So this would be another example of where you want to do an indirect proof, because it's rather obscure for a conventional two-column direct proof. So what we're going to do then is start by assuming that n is even, right? Assume the opposite is true. Assume n is even. Then n squared is even, right? Because if you take an even number, and you square it, you're going to get an even number, aren't you? So assume n is even, then n squared is even. But this contradicts n squared is odd. Therefore, so this little three-dotted triangle symbol I'm drawing means therefore. That's how you can say therefore. It's much easier than writing it out, isn't it? Just a three-dotted triangle symbol that means therefore. Therefore, n is odd. So let's go through this indirect proof again. So we're given n as an integer. No matter what we do for the indirect proof, whether it's even or odd, it's always an integer, right? That won't be contradicted. But what they give us is that n squared is odd. That's the second piece. We have to prove that n is odd. So we start by assuming the opposite of what's to prove. We assume that n is even. Now, you know, again, if you take an even number and set it to the second power, you're going to get an even number. Then n squared is even. But this contradicts n squared is odd. Therefore, n is odd. So we assume the opposite of what's to prove. And then we made an example out of what would happen if n was even, then n squared would have to be even. And then we showed that it contradicted a given statement. It contradicted a given statement. So therefore, by that logic, n is odd. It must be odd, right? So that's all you're doing for indirect proofs. All right, what's next? Let me draw my diagram here. Yep, I'm doing that on purpose, actually. Here's line A, here's line B. Here's transversal T. Let me write in red here so you can see it. Angle 1, angle 4. angle 3, and then angle 2. Alright, so this is going to be an interesting one. We are given, in this particular case, transversal T cuts lines A and B. We're also given that the measure of angle 1 does not equal the measure of angle 2. We have to prove that A is not parallel to B. So you see how obscure this really is, why a direct two-column proof would not work in this particular case. It's easy to prove something's parallel, but when you try to prove something's not parallel, that's a little bit harder. So we're given transversal T here cuts lines A and B. We're also given that the measure of angle 1 is not equal to the measure of angle 2. We have to prove that A is not parallel to B. So here's how we're going to start for an indirect proof. Assume A is parallel to B, right? Assume A is parallel to B. This would mean angle 1 is congruent to angle 3 by corresponding angles are congruent. So we started by assuming that A is parallel to B. Assume the opposite. Well, then we say, what does that really mean? This would mean that angle 1 is congruent to angle 3 by corresponding angles are congruent, right? Angle 3 is congruent to angle 2 by vertical angles are congruent. Well, whether these lines are parallel or not, 3 and 2 are vertical angles. That much is true. That much is absolutely true. Then we could say by the transitive property, angle 1 is congruent to angle 2. Now you see the contradiction. By the transitive property, we could say angle 1 is congruent to angle 2. But this contradicts. We have a contradiction here of a given statement, but this contradicts the measure of angle 1 does not equal the measure of angle 2. Therefore, A is not parallel to B. We can soundly say now that A is not parallel to B. So let's go through this indirect proof. We were given lines A and B, both cut by transversal T. That, of course, was in the given. We're also given that the measure of angle 1 does not equal the measure of angle 2. We're tasked with proving that A is not parallel to B. So you start by assuming the opposite of what you set out to prove. Assume that A is parallel to B. This would mean that angle 1 is congruent to angle 3 by corresponding angles are congruent. Remember that postulate that whenever you have two parallel lines cut by a transversal, corresponding angles are congruent. Okay? Next, we could say angle 3 is congruent to angle 2 by vertical angles are congruent. That's true regardless of whether these lines are parallel or not. Vertical angles are congruent. Then, what that would mean is by the transitive property, angle 1 is congruent to angle 2. But this contradicts the measure of angle 1 does not equal the measure of angle 2. Therefore, what we set out to prove must be true, that A is not parallel to B. So sometimes indirect proofs are nice, but we're not going to use these a whole lot. This will probably be the only lesson we really use them on. I still have to teach it. It is a useful tactic sometimes, especially when you get into number theory problems or really obscure geometry. It can be useful. Okay, let me draw something here. I better make that a little bit bigger. I'm doing this for an audience. I better make this a little bit bigger. Okay, we'll do that, no problem. Alright, what do we got here? What do they label this one? Huh, joke. That's funny. This is quadrilateral joke. I like that. With, they also give us angles 1 and 2 right here. So let's see what they give us in this indirect proof. We are given that segment OJ is congruent to segment OK. We're given that. What we're also given is that JE, segment JE, is not congruent to segment KE. So that's going to become very relevant in just a minute here. We have to prove that ray OE does not or doesn't bisect angle JOK. So another obscure geometry proof where it would pretty much be impossible to use a direct proof. So we're given to start with that OJ is congruent to OK. In fact, if you want to mark that on your diagram, I would encourage you to do so. We're given that JE is not congruent to KE. What we are seeking to prove by indirect proof is that ray OE doesn't bisect angle JOK. So, of course, like you would with any indirect proof, start by assuming the opposite of the conclusion. So, assume ray OE bisects angle JOK. All right, so we just stated the opposite of what we're seeking to prove. So what does that mean? This means angle 1 is congruent to angle 2 by definition of angle bisector, right? We want to say why that is. This means angle 1 is congruent to angle 2 by the definition of angle bisector. Then we can say that OJ is congruent to OK. You can use given information in your indirect proof. That's just fine. And OE is obviously OJ is congruent to OK. Let's separate that a minute here so it'll make more sense. By given info, we'll just say info, OE is congruent to OE by reflexive property. So what does that mean? If we're going on the assumption that OJ is congruent to OK, angle 1 is congruent to angle 2, and then OE is congruent to OE, this means, so in each triangle then we would have a side angle and side congruent. This means by side angle side theorem that triangle OJE is congruent to triangle OKE. So now that we've proven congruent triangles, this means JE is congruent to KE by CPCTC. Corresponding parts of congruent triangles are congruent. So now we just made a contradiction that JE is congruent to KE by CPCTC. But this would contradict JE is not congruent to KE. So now we've established that we have a contradiction. Therefore, what we're trying to prove must be true, that therefore ray OE doesn't bisect angle JOK. Alright, so let's go through this indirect proof again. We're given two triangles connected, right? That are connected to form quadrilateral JOKE. They give us that OJ is congruent to OK. They even give us that JE is not congruent to KE. What we are seeking to prove is that ray OE doesn't bisect angle JOK. So we started by assuming the opposite of the conclusion, which is what we're seeking to prove. We assume that ray OE bisects angle JOK. So what does that mean? This means angle 1 is congruent to angle 2 by definition of angle bisector. OJ is congruent to OK by given info. OE is congruent to OE by the reflexive property. All these facts together means by the side angle side theorem that triangle OJE is congruent to triangle OKE, which in turn means that JE is congruent to KE by CPCTC. However, but this would contradict that JE is not congruent to KE. It contradicted given information. Therefore, ray OE doesn't bisect angle JOK. In other words, therefore, what we're seeking to prove must be true since we contradicted a given fact. That's all that's saying. I know these are a little bit different than proofs you're used to, but when you get used to them, in some ways these are easier than the proofs we've done. Because all you have to do is show one contradiction and it throws out your assumption and enables you to prove what you were trying to prove. Alright, what do I got here? I just got two more and then we're done for the day. Let's lower this a little bit. Let's lower this a little bit. There's a reason I'm doing this. Let's even bring in one of these. Yes, there's a reason I'm making a big mess. Don't worry. I have a purpose for it. Okay, so this is plane P. This is plane Q. What's the next plane called? They don't give it, but... Oh, this is plane N up here. There's plane N. These points where plane N touch are A and B. The points where plane N and plane Q touch are C and D. Okay? So far we have a diagram with planes P and Q cut by transversal plane N. The point where plane N meets with plane P is at the segment AB. The segment where plane N meets with plane Q is at the segment CD. So far we see that. What are we given? We are given that AB, that segment AB, is not parallel to segment CD. Right? What are we to prove out of this? We are to prove that planes P and Q intersect. So we're given that segments AB and CD are not parallel to each other. We have to prove that planes P and Q intersect. All right, so we start out by assume planes P and Q don't intersect. So we're going to start out by assuming that planes P and Q don't intersect, right? Well, what does that mean? This means plane P is parallel to plane Q, right? So far, if planes P and Q don't intersect, the only other option, if they don't intersect, that means planes P and Q are parallel to each other then. Okay. This would make AB parallel to CD due to the fact that if two parallel planes are cut by a third plane, then their lines of intersection are parallel. So far we assume that planes P and Q don't intersect. This means planes P and Q are parallel to each other. This would make lines AB and CD parallel to each other due to the fact that if two parallel planes are cut by a third plane, then their lines of intersection are parallel. That's where we could draw the conclusion that AB is parallel to CD. But this would contradict that AB is not parallel to CD. Therefore, it must be true that planes P and Q intersect. So let's go through this indirect proof here. We're given that lines A, B, and C, D are not parallel to each other. We have to prove that planes P and Q intersect. So let's start by assuming temporarily the opposite of this is true. Let's assume planes P and Q don't intersect. Well, that means that plane P is parallel to plane Q, right? If they don't intersect, the only other option is they're parallel. This would make lines AB parallel to CD due to the fact that if two parallel planes are cut by a third plane, then their lines of intersection are parallel. That's a previous theorem that we learned earlier in the course. But this would contradict that AB is not parallel to CD. Therefore, since we've shown the contradiction, planes P and Q intersect. That's all we can do for that one. And I got one more example, then we're done. Okay, what did they give us for the last one? This is A, B, C, T. All right, this has a length of 5. Hold on, I got that backwards here. 1 second. I got my labeling backwards. I drew the diagram right, I just didn't. A, there's T, there's B, there's C. Okay, we're good now. Now I got it correct. So AT is 5, BT is 5, but CT is 4. So this is an interesting proof. What are we given this time? We are given that AT equals BT, which equals 5, right? So AT equals BT, and they both equal 5. We're given that CT equals 4. What are we to prove? We have to prove that angle ACB is not a right angle. So very interesting proof here. We're given here that AT equals BT, which equals 5. So heck, let's play some congruency markers here even, if it helps you. We're given CT equals 4. We have to assume then that angle ACB is not a right angle. So let's go ahead with the indirect proof. And as you know, we start first with assuming the contradiction of what we're trying to prove. Assume angle ACB is a right angle. So we're going to start by assuming that ACB is a right angle. This would make triangle ABC a right triangle. So yes, if angle ACB was in fact a right angle, this would make triangle ABC a right triangle, would it not? Okay. From there, all right, so since AT equals BT, T is the midpoint of AB, of side AB. Which that would be true. If AT equals BT by the definition of midpoint, then you would have that T is the midpoint of AB, right? Because you have two congruent segments. Now, what we're going to say next is, by this theorem here, by the theorem that the midpoint of the hypotenuse of a right triangle is equidistant why are you fading? There we go. From the vertices of a equidistant from the vertices CT equals 5. So let's talk about where we're at so far. So we're assuming that angle ACB is a right angle. This would make triangle ABC a right triangle. Since AT equals BT, T is the midpoint of side AB, right? Which, by the definition of midpoint, that'd be true. So, again, assuming then that this is a right triangle, by the theorem that the midpoint of the hypotenuse of a right triangle, because AB then would be your hypotenuse if ACB is a right angle, right? By the theorem that the midpoint of the hypotenuse of a right triangle is equidistant from the vertices, then CT is 5. So in other words, if this were a right triangle, yes, AT would be 5. It would be equidistant from A to B to C. So BT would be 5, but if this were a right triangle, CT should also be 5, right? But this contradicts that CT equals 4. So we've established the contradiction that it's that what we got, CT equaling 5, contradicts that CT equals 4 in the given information. Therefore, angle ACB is not a right angle. So ultimately we've proven that the conclusion must be true, that angle ACB is not a right triangle. So let's go through this one again. We're given triangle ABC up there, right? We're given that T is the midpoint of side AB because AT equals BT, which equals 5 on each side. Then we're given that CT equals 4. What we're ultimately setting out to prove is that angle ACB is not a right angle. So we're going to start by assuming that angle ACB is a right angle. Well, this would make triangle ABC a right triangle then, right? If you have a right triangle, if you have a right angle in a triangle, that makes it a right triangle. Since AT equals BT, T is the midpoint of AB by the definition of midpoint. So, if we're assuming then that this is a right triangle, that means angle ACB is a 90-degree angle, and we know the side across from the right angle of a right triangle is called the hypotenuse. This would make AB the hypotenuse. So by the theorem that the midpoint of the hypotenuse of a right triangle is equidistant from the vertices, CT equals 5, right? T should be equally from A to B to C. And we got that with AB, but that also means that CT should be 5. But this contradicts that CT equals 4. So therefore, what we're trying to prove must be true, that angle ACB is not a right angle. So that's really it for indirect proofs. This will be really the only lesson we do on them, but this is a good type of proof to keep in your toolbox in case you're ever faced with some really obscure thing you're trying to prove that there's no way you could prove with a direct proof that we've normally done. But ultimately follow what your teacher told you, because I'm here to help you, but I am not the replacement of your teacher. So always follow the method your teacher told you to do. So next lesson we're going to get into inequalities for one triangle. I hope everyone has a great night. Take care.